Recent findings in astrophysics suggest that our solar system's unique structure and characteristics may be the result of a dramatic interaction with a passing star billions of years ago. This stellar visitor might have ventured close enough to our young sun to significantly influence the distribution and orbits of celestial bodies in the outer solar system. The gravitational effects of this close encounter could have redirected countless objects from their original positions, drawing some closer to the inner regions and even helping to create the complex orbital patterns observed today among trans-Neptunian objects and the irregular moons of the gas giants. Such an event may provide answers to some of the most persistent questions about our solar system structure and dynamics, revealing a history shaped not only by internal processes but by external stellar influences. To understand the gravity of this potential event, it's essential to look beyond the traditionally understood boundaries of the solar system. While many people think of the solar system as extending outward to Neptune, or perhaps even Pluto, modern astronomy views its outskirts as extending far beyond that to include two remote regions known as the Kuiper Belt and the Oort cloud. These regions are populated by icy bodies and comet-like objects, many of which orbit at extreme distances from the Sun. The Kuiper Belt lies just beyond Neptune, while the more distant Oort cloud forms a spherical shell around the solar system, possibly extending up to a light-year away. For many years, these regions have been regarded as the source of long-period comets and other icy wanderers, with many of their members appearing to follow oddly shaped, eccentric orbits that suggest an unseen gravitational force has disturbed them in the past. Understanding the origins and current structure of these regions has posed a puzzle for astronomers, who have searched for explanations for the strange paths followed by many of the bodies within them. The idea that a passing star could explain these irregularities has been gaining ground thanks to the work of astronomers like Suzanne Fair and her team at the University of Leiden in the Netherlands. Fair and her colleagues have conducted more than 3,000 computer simulations to explore the potential effects of a close stellar flyby on the solar system. Their results suggest that a single encounter with a star about 0.8 times the mass of our Sun could account for many of the observed anomalies in the outer solar system. According to their simulations, this star likely approached our Sun at an angle of about 70 degrees relative to the plane of the planets, passing within approximately 16.5 billion kilometers, or about 110 astronomical units, AU. To put this in perspective, $1 Australian represents the average distance between the Earth and the Sun, or roughly 150 million kilometers, which means that this stellar visitor came closer to us than the present positions of the Voyager 1 and Voyager 2 probes, which are now exploring the boundary regions of interstellar space. One of the primary consequences of this encounter would have been gravitational disruption. The simulations show that the flyby could have set off a gravitational chain reaction, pulling objects in the outer solar system out of their original orbits and scattering them in various directions. Some objects may have been ejected entirely, thrown out of the solar system to drift through interstellar space. Others may have been flung inward, crossing paths with the gas giants, where they might have been captured as moons or redirected into elongated orbits that now define some of the most distant objects observed in our solar system. This scenario provides a straightforward explanation for the prevalence of retrograde moons around planets like Jupiter and Saturn. While many moons orbit their planets in the same direction as the planet's rotation, a pattern known as prograde motion, Jupiter and Saturn are each accompanied by a surprising number of retrograde moons, which orbit in the opposite direction. Astronomers believe these moons are likely captured objects, their retrograde orbits a signature of their origins as interstellar wanderers or distant solar system bodies caught by the giant planet's gravity. At Jupiter, for example, researchers have identified 71 retrograde moons compared to only 16 prograde moons. Saturn displays a similar pattern, with 100 retrograde moons and only 22 prograde ones. Uranus and Neptune also possess large numbers of irregular satellites with eccentric orbits that don't conform to the traditional patterns seen in the inner solar system. By stirring up the outer solar system, a passing star could have flung objects inward, allowing the gas giants to capture these celestial bodies and creating the unusual satellite distributions observed today. According to Fair and her team's simulations, as many as 7.2% of trans-Neptunian objects may have been moved inward by the star's passage, and of these, many would have been captured by the gas giants as moons. These captured objects are far more likely to end up in retrograde orbits than in prograde ones, which matches the observed distribution among the outer planets. The star's influence might also help explain the unusual orbital characteristics of specific distant objects, like the dwarf planet Sedna. Discovered in 2003, Sedna follows a highly elongated orbit that takes it as far as 1,000 Australian dollars from the Sun, a journey that places it well beyond the more familiar confines of the Kuiper Belt. Its orbit has puzzled astronomers because it's difficult to explain how an object could end up on such a distant, elliptical path without external influence. However, the simulations indicate that a close stellar flyby could have pushed Sedna into its current orbit, along with other objects that follow similarly inclined and elongated paths. In fact, the star's gravity might have been powerful enough to generate the population of scattered disk objects, which includes a number of other bodies with strange orbits that don't fit neatly within the standard models of planetary motion. Another important impact of this stellar encounter could have been on the mass and distribution of material in the Kuiper Belt. Current models predict that this region should contain a substantial amount of mass, potentially as much as several Earth masses worth of icy bodies. However, observations indicate that the actual mass of the Kuiper Belt is only about 1% of these estimates. This discrepancy has been a long-standing mystery, but Fur's team proposes that a close pass from a star could have stripped away a significant portion of the Kuiper Belt's material, scattering it into interstellar space and leaving behind a much more depleted population than originally expected. This mass loss would not only explain the discrepancy in the Kuiper Belt's current mass but would also account for the presence of two distinct populations within the belt, the cold, classical Kuiper Belt objects, which follow more stable, circular orbits, and the hot population, whose members have more eccentric, inclined orbits likely due to past gravitational disturbances. Fur's simulations reveal that this single stellar flyby might also explain other fundamental features of the solar system, such as the mass difference between Uranus and Neptune. These two ice giants are similar in many ways, but Neptune is significantly more massive than Uranus, a characteristic that has puzzled astronomers for some time. The passing star may have disrupted the accretion of material around Uranus, limiting its growth while allowing Neptune to amass more mass. Additionally, the flyby could have contributed to the separation of the Kuiper Belt into two populations, as some objects were scattered into inclined orbits while others remained in the main plane of the solar system. This star passage hypothesis also aligns with another close encounter Fair and her team studied, which could have occurred over 4 billion years ago when the solar system was still in its early stages of formation. During this time, a star of between 0.5 and 1 solar masses may have passed close enough to affect the outer edge of the solar nebula, the vast cloud of gas and dust that gave birth to the Sun and planets. As the star passed by, it likely stripped material from the outer regions of the nebula, potentially influencing the formation of the Kuiper Belt and Oort cloud, as well as the masses and positions of the outer planets. The timing and scale of this earlier encounter align with models suggesting that such a passage could have shaped the solar system's current configuration, helping to explain not only the eccentric orbits of trans-Neptunian objects but also the distinct compositional differences between the Kuiper Belt and the inner solar system. Thanks for joining us on this fascinating journey through the cosmic mysteries that continue to shape our understanding of the solar system. If you enjoyed exploring these incredible theories about our solar system's origins, be sure to hit that subscribe button and stay tuned for more amazing insights. Here at Space Lab, we're dedicated to unraveling the secrets of the universe, one discovery at a time. Don't miss out on our upcoming episodes where we dive even deeper into the wonders of space.